Is joint work that I've been working on for a while now with a student in the Electrical and Computer Engineering Department, AA, Eric Miller, and Arvind Saibaba. I do have one affiliation up here besides just my Tufts affiliation, so just for a moment with that hat on. I am currently a Deputy Director for the Institute for Computational and Experimental Research in Mathematics at Brown University. And I would love to invite all of you to, look up what kind of programs we're having if you'd like to come to Brown, which is in Providence, or if you want to propose programs, please come talk to me. So, without further ado, let's see if I can get this slide. That's great. So I didn't want to assume. I wasn't sure who was going to be in the audience. So I didn't want to assume too much. I will spend just a little bit of time talking about the formulation for the inverse problems and the notation and so forth, what my motivation is for studying this type of reconstruction. Go over the notation and the background so that we can all be in the same speed. And then the starting point for this is some work that I did a little over 10 years ago with parametric level sets, or PALs. And that was for binary images, and tell you where the advances have been in coming up with this new PaLENTIR model, which is really good, it turns out, for addressing multiple contrasts. I'll show you several numerical experiments and talk about what we're doing moving forward. So again, what I want to be clear from the first few slides is that the method that I'm proposing is going to be useful whether you're talking about a linear inverse problem or whether you're talking about a nonlinear inverse problem. So for a standard example of a linear inverse problem is the problem of Deblurring. Right? This is an example where I've taken an image of my daughter some years ago and done a 2D convolution. Of course, we know what the blurring operator is. We have the measured noisy data, and we'd like to reconstruct an unblurred image. And the unknown in that case is simply, it's a grayscale image, so it's simply intensity values. The inverse imaging problem of most interest to me that's nonlinear is a problem in diffuse optical tomography, where here the idea is you're shining near-infrared light through tissue. That light diffuses through the other side. We tend to use this for things like looking for tumors in breast tissue. And so in that case, we're really just interested in coming up with where is this anomalous region in terms of the absorption coefficient. And that is our image. Of course, it would be a 3D image in that case. So in this case, the forward model depends on being able to solve a diffusion equation for lots of sources at lots of different detectors. And so here, the actual PD model depends on your current estimate of what that image would look like. It's a nonlinear problem. So just to keep things simple, I'm going to assume just a straight, like a finite difference approximation. Ideally, we just think of discretizing this forward problem, discretizing the thing that we're looking for, this f of r, and we're going to instead think of just finding values of f at some discrete points, r sub I. And of course, even if the forward model is good, in reality, the actual measured data is noisy, so D has some noise in it. The noise is unknown. We know some things about it, but not much. In the best case, if this is a linear problem, it's full rank, but an ill-conditioned matrix. And in the worst case, it's really underdetermined, very data limited. And that's going to be the case for some of the examples that I show you later on. As soon as we start talking about regularization, most people are familiar with this sort of Tikhonov regularized approach, where you take the data misfit term, this is in the linear case, and tack on some kind of regularization term. So the regularization term is meant to enforce some kind of a priori knowledge that you have on the solution. This magical number lambda here is the regularization parameter. It tends to tell you how to balance this a priori information against the misfit. I tend to think of choosing this regularization term as an application-specific art form. So if you're working on a specific problem, it does take a lot of finesse to kind of, in many cases, get the right choice for what that operator R should look like. And certainly, if what we're interested in, as I am, is getting images with lots of sharp edges and boundaries, then this thing sometimes will add to the computational complexity then. So this might be a 2 norm, but this might be something much more ugly in terms of an optimization problem that we then have to solve. And so, and then on top of that, we have this issue of the regularization parameter selection. So all the people that are in the room that have a lot of experience with solving inverse problems know just how annoying it is to try and find the right value of the regularization parameter and the additional computational expense that is involved there. So what I'm talking about today is a method that we think is going to be valuable for the classes of problems where the unknown quantity of interest is really well modeled by a piecewise constant in 2 or 3 dimensions. So instead of tacking on the regularization to the cost function, what we're going to do is build the regularization into the parameterization of the unknown quantity. This approach means then that it will be independent of the forward model operator. I can use it for linear and nonlinear. The model is basically agnostic to the spatial discretization for the forward operator, which is also very nice. And then the optimization problem, recovering the image, is one of just recovering the parameters that define this unknown quantity, and that gives us a better posed optimization problem. So my notation for this is that D is my data. This script M just denotes my forward model mapping from the unknown quantity of interest, and here I've just written it in the continuous form. You'll see why in a few slides. R is a spatial variable, so it's either 2D or 3D quantity, and W in this case represents unknown noise. I am assuming that it's Gaussian white noise. However, I think we've done some examples that suggest that we don't really need this restriction at all either. Okay. As I said a few moments ago, my assumption is that the desired unknown is a piecewise constant with a modest number of unknown contrast values and shapes. I do not know the shapes. I do not know the number of contrast values. That's something that we're trying to learn from the process. The forward model can be linear or nonlinear and should work in the case quite well when we have limited data. So I am going to still be trying to recover an image, but I'm doing that through basically finding the parameters that describe this reconstruction. So in the case, for example, I talked about diffuse optical tomography, it's really, it's just not necessary to solve for, an exact value in every voxel of my image. I really only need to know where that tumor is. And so this is something that can work well in such a situation. So the first thing that one might think of in terms of doing something like this is, okay, if I assume the simplest case, my image is just binary. It's piecewise constant with one transition. If I have an indicator function chi of D, and I'm thinking of in this region D, chi takes on the value of 1, and outside the region it takes 0, then the way that I could express this is that my unknown quantity can be some value inside my object times this characteristic function, or a value outside the object times 1 minus the characteristic function. So I could find this image if I could describe the boundary of D and if I knew these two values. So a method for doing this kind of representation, at least in the context of imaging, was proposed by Santosa and others back in '96. This is, I'm thinking about the traditional level set approach, where you basically have some surface function. In the trying to get 2D images, it would be a surface here. And if I cut that at, say, the 0 level set, then I will get a 2-dimensional image, right? So cutting this, finding the level set, will give us basically the boundary information that we desire. And here I've just shown these 3 surfaces that I've changed modestly, and then you can see the impact on the corresponding images you could get. 2 disconnected things, something touching at a point or whole shape. So the idea with this approach is, okay, this is topologically really flexible. We just evolve this function. We pick the right number of connected components by minimizing the cost function. Easy. This has been used successfully in, successfully, quotes, for inverse problems in practice. There's a lot of work that I haven't mentioned here. This is just a sampling and the applications in which they've been utilized. But, here's a but, highly non-trivial to do this for inverse problems. If you think about this, especially in the data-limited case, we have noisy problems opposed or at the very least ill-conditioned, right? It's really non-trivial to think about how to evolve this surface in that context. You have to pay attention to a speed function, how you initialize the surface. There are issues about rates of convergence. Regularization is just going to be needed. There's just too much freedom in just saying, I just want a level set of any old surface, right? And then you have to think about, how do we tailor the optimization so that we can get it to work efficiently.
So it's just allowing kind of parameterization of triangle.
So I'm not even imagining a parameterized surface. It's just any surface that I'm just evolving. So that's exactly what the problem is. There's too much variability, right? So that's why you would need some very specific regularization in this other case to try and make that surface go towards something that makes complete sense. So what we decided to do, this was just over 10 years ago, was work with parametrically defined surfaces, and then we will solve for the parameters. One other thing, we're doing an optimization at the end of the day. You might imagine we're taking derivatives. Obviously, we're going to want to replace the actual Heaviside function, in this case, with some differential approximation. As I'll get to later on, the choice that we use for our approximate Heaviside function will be a key ingredient in being able to do this for multiple contracts. So the original parametric level set method, or PALS method, took this, for lack of a better word now, I'm calling it a landscape function. The O and the G just means it's the original kind of approach that we thought of. And the landscape function then is going to be a sum of capital N basis functions, a linear combination of capital N basis functions, phi j of r. So however these phi j of r are specified, they're specified in terms of a set of parameters. If I lump those parameters and the expansion coefficients together, those are the things that will allow me to specify the surface, change the surface, thereby changing the underlying image. Okay, so the property that I'm to be recovered is going to look like some value inside the object times a Heaviside approximation. I take the C level set, and a background value, which I may or may not need to solve for, times the converse. And so, again, the problem now becomes, we've substituted the problem of voxel-based or pixel-based image formation in terms of with parameters and values inside and outside the anomaly. What are the choices that will work here? Good choices in practice turn out to be radial basis functions. When we wrote the original paper that appeared in SIAM Journal of Imaging Sciences, we used compactly supported radial basis functions. And one of the reasons for doing those were that if you could use the compact support in a way such that it made the optimization problem easier in places where certain basis functions really weren't active. You could drop that information out of the Jacobian. So that it was nice in that regard. But several others have used just standard radial basis functions as choices. You could use sines and cosines. You could use polynomials. People have tried a lot of these things, but in the literature, they tend to gravitate toward the compactly supported radial basis functions or radial basis functions. The thing I want to point out is this capital N has nothing to do with the spatial discretization. It's just a choice. And the important thing is that it's small relative to discretizing all of pixel space or all of pixel space. If we had chosen a compactly supported radial basis function, and so these have depending on what you want, you can get higher and higher degrees of smoothness, but we tended not to do those too much smoothness in practice. But the idea is that you have some psi function and you apply it to this term right here. R, again, is the space variable, the chi sub j, the center location of the j basis function. The beta j acts like a dilation parameter. And this is a pseudonorm. So as soon as someone says pseudonorm, there's like a fudge factor, basically. And the fudge factor in there is to make everything so that I can differentiate and do the optimization problem. So the parameters here that I need would be all the expansion coefficients for all capital N of the basis, all N terms, all the betas, all the dilations, and all the center locations. So these blobs are allowed to float freely in space to give me this shape. And it turns out, since the time when we wrote the original work, we started to see this success for this in a lot of different applications. We have the specific references in our paper that's online now, but they come up in geophysics, electrical impedance tomography, acoustic scattering, and so forth. Use these successfully. So radial basis functions or compactly supported radial basis functions are really just bumps. They're round, so we cut them like this. The cross-section would be a circle. You might imagine that we want a little more flexibility, and there was some recent work that came out where they incorporated more rotational information in the 3D version of this. But it turns out it's a little bit tricky, and they still had to add additional regularization to get things to kind of go to the shapes that they were looking for. So what I'm going to do now is I'm going to abandon the compact support, and I'm going to abandon the pseudonorm in favor of both the flexibility and interpretability of just plain vanilla Gaussian radial basis functions. Use that for the jumping off point and show you what we can do. Okay. So simple Gaussian radial basis function is just this function here. And so now what I'm going to define in terms of my basis functions of interest, these psi sub j's are defined in terms of this Gaussian radial basis function applied to the 2 norm squared of beta j, which again acts like a dilation, the center locations, and so forth. So the original formulation, if I had used Gaussian radial basis functions again, would have looked something like this. And there's my stacked parameter vectors. Again, I said this earlier, but just as a reminder, if I have an underlying discrete grid, then my image at each one of the grid points is interpreted this way. And so I have this vector of unknowns, P, which is in 2D length 4 times capital N, or 5 times capital N, relative to little n, capital N points, right, which is going to be large in a lot of these applications. So the optimization problem now is really simple, right? I can just write it down like this. Non-linear least squares problem, right? You know how to solve non-linear least squares problems, more or less. It does turn out that you need a little bit of finesse. You don't just take your Levenberg-Moore part off the shelf and do something. You know, we use something called a trust region regularized Gauss-Newton approach to do this a little bit better. But I'm not using any other regularization. Okay? Regularization is built into the parameterization of the image space. And if I didn't know the object's value in the background and in the foreground, I could solve for those values as well.
Is there anything stopping the kind of Gaussian blobs from kind of just occupying the same area?
Yes, thank you. Limitations. Nice segue. First, it's limited to binary images. So the straightforward fix that was proposed back in one paper in 2016 turns out to be pretty expensive, right? You can think of, well, I need another kind of instance of this for each object that I want to represent, and then I also have to know how many contrasts I'm solving for, so that's bad. But the problem still is that similar shapes, so similar of these surfaces, give, with very different parameters, values, can give rise to the same image, right? Because at the end of the day, you're taking this Heaviside approximation, cutting through the surface. So the surface doesn't care if, you know, your kind of circular-looking thing is defined in terms of one blob, multiple blobs lying on top of each other, very close to each other, a very high amplitude, or, you know, different dilation coefficients. So this issue where we're allowing the centers to float does add also some indeterminacy, because the blob that started here could move here, but the blob that started here could move here, and yeah. So that's exactly what you're getting. So this leads to some ill conditioning with the Jacobian that, you know, we can kind of get around, but is annoying when we try to do problems like uncertainty quantification. And I've only talked about radial basis functions, but of course you can imagine we would want to capture elongated shapes, and that would take many, many basis elements to do accurate. So now I get to the heart of the matter. This is our newest fix. So now you can see where the acronym came from. I'm absolutely hopeless at coming up with good acronyms, so this was all Eric's doing. Maybe some of you know where this is. He really likes what's that? Lord of the Rings. Yeah, it's like a Lord of the Rings thing. So anyway, the PaLENTIR model features, in this case, we're not going to float the centers. We're going to put the centers on a fixed grid. That will already eliminate 2n or 3n unknowns, makes the optimization problem easier. We're going to add a transformation, a sort of a shearing, special type of shearing transformation that allows us to capture elongation. We're going to bound the weights in the front, so we can't have amplitudes spiking way, way high when we could get the same object by keeping them within a bounded range and just changing dilations. And I'll show you that if we add a certain amount of spatial dependence to the background and the object contrast values, we can actually come up with a reconstruction that allows multiple contrast image with a single set of basis functions. So just to put them side by side, this would be sort of the traditional radial basis function approach in the literature. In 2D, what we're doing looks like inserting, instead of beta j, we have this rj. So you can see it's a kind of a shearing transformation. It's still dependent on a value beta j and value gamma j. The chi j's, again, they're arranged on a fixed grid. So they're not treated as unknowns, but this grid where these basis vectors live, they live in the domain of interest, of course, but it doesn't need to know where you have discretized your forward problem, which is kind of neat. It keeps these things decoupled. Mu, it's a fixed scaling parameter, depends on properties of the grid spacing. We know some ways to choose it, but for purposes of this talk, I'm not. The other thing I said I was going to do was to bound the weights. So instead of just solving for alpha j, or I'm still solving for an alpha j, but here I'm going to put alpha, the expansion coefficients, into this function here, and that ensures that the weights of the basis function are bounded between -1 and 1. So that helps with the stability. Now, so far, this is where we are. I've got a Heaviside function approximation. If I'm doing the 0 level set, then this is what my model now looks like. I have this value inside, this value in the background, and if I can recover the parameters and possibly also these values, I'm done, at least for a binary. So the thing I haven't talked about yet is this animal here, H sub epsilon. And it turns out there are good reasons to think carefully about your choice. So to get to the point of multi-contrast, I'm going to do this in stages. First, let's assume that I just have a 0 background. All I want to do is and I assume I know what the value is inside the blob. So I need an approximate Heaviside function, and this is the animal that I'm using here for that. And here is my, the way I'm describing my surface. The parameter epsilon here actually controls the sharpness of the transition. It turns out we can take advantage of the transition to get multiple contrasts. And so that's what I want to kind of trace through. So let's do this for a very, very simple case. Here is my true image. My forward model, it's just an identity operator. So this is just, can I find this parametrically defined image using this formulation? Can I throw this into the optimization and recover anything useful? So this image of the squares was not made with these bases. It was just hand-tuned for different contrast values on a 0 background. Here is the PALS fit, and you can see that the yellow block is very sharp, right? And that's the one that corresponds to the value of C high that I said was known. But I get pretty good shape, estimates for where these things are. They just look a little bit wiggly, and the question is, what's going on here? Why did I even get those back?
This palette fit is only using a method that's intended to capture 2 contrasts? Or?
It was originally intended just to capture, basically something on unknown background, basically just 2 contrasts. Binary.
But it still gets all 4.
But it gets all 4, and this is the reason, right? So if I look at how I chose the Heaviside approximation here, the H epsilon, this is the graph of an H epsilon. So if I should have put vertical lines in here, probably it would have been easier to read. But here's point 2. I draw a vertical line up here. If phi of r is greater than 0.2, you can see that the Heaviside approximation is close to 1, the heaviside approximation in the model was multiplied by C high, right? C high, there. So that's why you get the 4. But if I'm, say, close to 0, so here's 0, trace it up, then if phi sub r is close to 0, the heaviside approximation is, in this transition region is 0.5. 0.5 times 4 is going to give me 2, so that's how I get the intensity 2 image. Down here, just to the left of 0, trace it up, right? If it's close to like minus 0.05, the H epsilon is 0.25, so 0.25 times 4 gives me the image intensity 1, and one of those was at 1. And then if it's down here in value, then I get something close to 0. This is the actual mesh plot of the surface function, which we're taking a look at. You can kind of see here the largest corresponds to the largest blob, and it doesn't care that there's the hilly landscape, because at the end of the day, that's all stuff that's out over here, and it's locked up. So this we found kind of by accident. Oh, isn't that a happy accident? Isn't that how mathematics goes sometimes, a happy accident?
It's kind of behaving itself when the intermediate ones in a nice way.
You're right.
But it doesn't matter, does it? As you say, on the one that's 4, the hills above the level set for 4 are completely irrelevant, so it's not trying. They'll just do what they like.
Yep. So it's really because this H epsilon thing is not sharp, completely sharp, that these other contrast regions can actually be observed. We didn't notice this at first because we had approximations that were, really, really sharp. We were trying to approximate the heaviside function and get this. And, if I want to just adjust for non-zero background, there's really nothing left to do. So that's the next level of interest would be to do this. So if I know C high and C low, then, I've got the ability to get sort of multi-contrasts within this region. But could I get, well, let me go back, right? So you do see these shapes, we do get them, but they're not sharp. This one is the one that's sharp, and it's sharp because, if you look at the surface and we cut across the surface, right, everything's like pretty much above that, you get nice sharp edges. So our idea was, what if we could get a loose idea, we could learn a loose idea of what the C high and the C low values were as a function of space through an iterative type process. Could we expect to do better? So in this case, it changes our model a little bit. We have this, but I just want to make it clear that a low resolution choices for these things will work well. So I want to try and show you the impact of the inclusions using some hand-chosen versions of these things. Okay. So I show out for each one of the next 3 slides, I made some choices for this, and then I solved this problem, again with M as the identity operator and Gaussian noise. See what would happen. So if this is the distribution for the lowest possible value, and this is for the highest possible value, here is a reconstructed image, a different image, basically. And you can see that, here this object is pretty sharp, and it's almost exactly the right value. Likewise, this circle is very sharp. But things over here and over here are still a little bit wiggly and blurry. So I don't change this distribution, but I do change this distribution, and you can see the improvement to both regions. And if I now change the distribution for C low as a function of space, you can see that I get its sharpness. So this is what I meant by it's like a coarse approximation to what the upper and lower bounds ought to be for that region in space. So in practice, we're going to dynamically do this, right? We're going to start with some estimate of what the highest and the lowest values are, constant images. We solve for this thing with this trust region regularized Newton approach. And then we do something where we just plop a little window, we visit every pixel, we look, it's in this region, we find the max in the window, we find the min in the window, and if the changes from the current pixel value are more than 2%, we just update them with the current max and min values and move on. So it's fairly straightforward. So if I run the algorithm that I just mentioned on the same image, then here's what I get. So there is a final C low distribution. You can kind of see shapes in there, a final C high distribution, and that's our PaLENTIR. Again, there's no inverse crime. I didn't make this image using these parametric level sets. So, okay, that was the identity operator. Let's go back to some real inverse problems and see what we can get. So here, my first example is using deblurring. So it's just a Gaussian blurring kernel. Again, I'm starting with a synthetic image. It was not used, it was not formed using any PaLENTIR model, so I'm not committing an inverse crime. I added noise to this. And what I'm going to compare it to is one of these Tikhonov regularized things where the regularization operator is something called total variation. Many of you are familiar with that. And I threw thousands of choices of lambda into this routine and picked the reconstruction with total variation that had the best value out of 1,000 choices lambda, and that's what we're comparing to. Keep in mind that we don't need to choose any regularization parameter. So here is the total variation reconstruction for this problem. It wasn't very blurry. This is, it does pretty well, but here's our PaLENTIR reconstruction. And I believe this was a 7 by 7 grid of basis functions. That's it. 7 by 7 grid of basis functions. So in other words, n is 49. Capital N, right? Relative to, I think this was an 82 by 82 image here. And you can see that our image in terms of PSNR, SNR, we're winning. Structured similarity measure, we're winning. Mean square error, we're winning. This, again, the best reconstruction over all these different choices of lambda. So it took a long time to really compute this. And this was sort of, we just set it and forget it, ran our algorithm.
Did you need to choose how many contrasts?
I didn't.
So
Nope.
it just picked its own.
Yes. Okay. So here is some Xray CT data. Again, it's real data, and you can go get this data for yourself. This is from their original paper, what they put as the picture of the ground truth image for this phantom. So it's a big block of cheese, and they carved the letters C and T out of it. In the paper, we have multiple tests with this, but this is, I'm showing the limited angle results for this. If you do Tikhonov reconstruction with a very simple regularization operator like 2 norm of the solution or 2 norm L time to solution, everything gets washed out in this direction. The people that are familiar with this kind of problem would expect this. Again, this is the best that we could, I guess, in terms of visual come up with for a total variation reconstruction, and here's our PaLENTIR reconstruction. I mean, you'd expect that there should be some artifacts because there are places where the data is just not existing. Again, we did not need to select any regularization parameter for our approach. And we investigated, you know, okay, if I do like 7x7, 8x8, 9x9 of these basis functions, how sensitive is it to that choice, right? Because you could implicitly think of this capital N as a regularization parameter. If you let that capital N go to infinity, this problem gets very ill-conditioned. You have too many parameters. It's really not so sensitive. So the reconstruction quality, if we used, you know, 6x6, 7x7, 8x8, 9x9L, pretty much look the same. If you started to use too many, it did get worse. We expect. In terms of sparse angle CT, we did the same kind of experiment, and again, we get nice, fairly clean results given the limited nature of this data. And this was again 7x7 grid with insensitivity to the total number of parameters there. And the last one, because I do want to convince you that this can work in the nonlinear case too, is this diffuse optical tomographic problem. So here, the way that we collect data is through this input-output map. And so this operator A of F of P, that's really the discretized diffusion operator given the assumption that this image gives you the absorption, right? So it depends on the values on the diagonal depend on the parameters. The B is basically a tall skinny matrix with ones and zeros. C is a tall skinny matrix with zeros. N is the total number of voxels or pixels, depending on 2D or 3D. And so if we want to think about what is the forward problem here, I basically vectorize this input-output map for specific instances. So every step of the optimization is going to require lots of PDE solves and lots of adjoint solves to be able to come up with what we need. So this is a 2D example, but what I want to drive home is the fact that we have limited sources on this side, limited detectors on this side, and nowhere else. So they don't exist over here and over here. And so you'd think that this would be hard. Light is diffusing in through the media from this direction. To really see this concave region in here should be very hard, and it was very difficult to do with our original version of PALS. But with PaLENTIR, with this image as my starting guess, so I set the parameters, and this is what the image would look like corresponding to the starting parameters. It's pretty constant. That's our reconstruction. And there was noise in the data. And I believe, again, this is probably about 9x9 in terms of parameters. Centers of where we start these things, again, do not have to live on the finite difference grid that we use to discretize the PD.
How long will it take to run?
For this, how long did it take to run? So we're sort of using a, I want to say it's kind of like a discrepancy when the residual flattens out, because at that point you've either hit the noise or you've hit model mismatch. So that's, I don't know, maybe 100 iterations or so. We can do this in 3D, because I know a lot of people are interested in 3D. And if if you think about this is probably not too surprising, right? These are different little shear things in the 3 different planes. And so I'm going to show you a reconstruction from a limited angle 3D parallel beam problem that, again, is available. You can get some of this stuff online. Our grid now is a 7 by 7 by 7 grid. And so this is 343 total unknowns versus 27 cubed voxels if I were going to reconstruct for every single voxel. It's a noise level of 1%. So we're using about a quarter of a sphere worth of projection information. So it's definitely data limited. The ground truth image, we played with this. So the point was to see if so in DOT, sometimes the problem is that if you have two objects, they kind of mush into each other. You really can't separate them. So we had two separate objects, and we wanted, so this was sort of a sphere-looking thing, and then something also with sharp edges. That's our PaLENTIR reconstruction. I don't even know if you saw me do that. Ground truth, PaLENTIR, right? And all those layers. And because I think it's cool to look at things in 3D, Ege figured out how to do this in a nice way. So this is just binary because, I don't know, that kind of complicated to think about how to show this for multiple contrast. But this is the ground truth, and that's our reconstruction. So we can separate them, and we can get very good edge information. So I think hopefully you're excited about what I showed you. I think we've developed this flexible parametric level set image model. It's agnostic to the type of forward problem. It doesn't care what your finite difference or finite element grid is, because it morphs on its own. We can get really sharp edges and detail with just a few basis functions on a fixed grid. And we can get multiple contrasts out of this as well. There's no regularization parameter to choose. I'm that's so happy. It does actually help us in terms of if we did this comparison of what the sort of conditioning of the Jacobian in the old PALs versus the new PALs, and we can show some improved conditioning, which is what we anticipated. We have some very 1D kind of, I think, theoretical convergence sort of results for this algorithm. We're really interested in hearing about the applications that you might have. And we have some MATLAB 2D code, which is easily adaptable to 3D if anybody wants to try it. One of the things that I've been thinking about trying for a long time is this, I think, really lends itself to adaptive refinement, all these kinds of properties that we have. Ege has got some results with sort of evolving these things over time, which is nice. So if you're trying to do space-time reconstructions, we can get some good things. We did a whole bunch of examples where we did just plain old denoising, and we weren't using Gaussian noise. And we could get qualitatively very good denoised results with this approach, even though our mismatched term was in a 2 norm. So we should look and see if whether this is a good thing to use for more general inverse problems when there's non-Gaussian noise. And of course, at the end of the day, we would really like to do some uncertainty quantification with this parametric approach, be able to say something about the quality of the reconstructions. We had done just a little bit with the PALS-based approach, but it turned out to be very, very hard, in part because of the indeterminacy that we had and the unconditioning of the Jacobians. But we hope with this formulation, be able to do something. So with that, thank you. Background is somehow this sinusoidal or something, right? You could parametrically define that background surface and kind of solve for those parameters. So that would work.
The regularization factor is oftentimes interpreted as prior. And you said that this is, you do the regularization by your parameterization.
Yes.
Do you have a sense of what that means in terms of
I mean, I think this is going to work where there are multiple well-defined contrast changes, sharp edges. It's not going to maybe work for, I wouldn't use this for just your general image deblurring and expect that it's going to, we have tried it like for the camera image, and you can see remarkably good things, but I don't think it's not necessarily.
Has it constrained the topology in 3D? Because you did have annular, someone can get that.
Yeah.
But in 3D, there's much more scope for weird topology. Would it handle that okay, or has it different some implicit parameters?
So we haven't had. We've only really tried this X-ray thing in the three-dimensional case. So and I mean, you saw kind of the results there again. As long as we are controlling that capital N relative to the available data, it's okay. If N would be too big, you get back to the same problem as you would have in any other case. You just can't fit that much information. So, but I hadn't really thought about the topology in my images.
Thanks, impressive results. So I guess a very applied question, which is, you say that it converges in 100 iterations or something like that, but how is the actual computational time for every iteration? Is it like way bigger than PT or?
So one of the things that I didn't talk about, so this trust region regularized Gauss-Newton approach, where we're solving for the parameters, we are computing a full Jacobian as efficiently as we can. It's a tall, skinny Jacobian because we have so few parameters. So that part, it makes it okay. We have a smart choice of directions in which we can search from there. You could imagine a scenario where the total number of measurements, sources, and detectors is crazy, and then even having this full Jacobian is maybe not feasible, so you have to do something else there, some kind of randomization or something instead. But for these problems, really wasn't any issue. Now I'm just doing them on my laptop, no out of memory error or anything like that. But of course, you have to set some things. This algorithm will it's set up so it will converge globally to a critical point, and we haven't had any problems with that. And then for every voxel, this averaging thing. I mean, obviously the work there depends on your window size and the total number of pixels, and you could probably do something even less precise than what we're doing and still get it.
So really big data sets, you can use a quasi-Newton method and a trust region framework
Sure.
as well.
Mm-hmm.
So,
Because we've got such an efficient representation of the solution, it's only like kind of hundreds of parameters, right?
Mm-hmm.
Example. Does that mean that you could have a decent shot at just shooting the hessian if you wanted to around the because then if you want to do uncertainty quantification, you could just attack it, that way. It's presumably
You're talking about when you get maybe close enough, then doing the extra work to actually compute the hessian close to
because that would give you correlations between
the stick.
You could probably follow through. It would give you correlations between the parameters that you use to parameterize the thing, and you could probably go. I'm never mapping from that to actual correlations between points in space or something like that.
I hadn't thought about that, but yeah.
Presumably, for this Gauss-Newton that you're using, you need to be able to do like a vis-directed natural derivative.
I'm sorry.
The forward map needs to be vis differential.
Yeah. Right.
Nobody's mentioned Bayesian, but it was sort of, I felt there's an open invitation when you said you and my thought is you've got a relatively low dimensional parameterization so that invites the possibility to do MCMC methods on those parameters.
Yeah,
is there anything wrong with that? I mean,
I don't think there's anything wrong with that, but so far the previous work that we were doing with the older method, we really only got as far as trying to think about, think of like the central locations of those things as the only unknowns we're solving. Some things, you can find some randomization techniques, but it turned out to be harder for some of the other parameters.
But there's also, as well as the parameters that are kind of made up for the level set, you could maybe think about if something has a purpose to do with the image, like count any connected components or estimate if two things are touching.
Oh, I see.
And
properties of the image
yeah,
that
maybe you could do
infer
that.
directly from this.
If somebody really knew what problem was they're trying to solve,
Mm-hmm.
perhaps you can put error bars on that. I don't know. It's an interesting.
That's interesting.
So I don't think we have any Zoom participants other than ourselves, otherwise we'd check for Zoom questions. I don't think we have any, but we're going to decamp to the first floor over in the new institute, and we have
There are some bottles of wine and some kind of soft drink organised by the institute.
Yeah,
Like,
we so we have an
carry all
informal
of it.
reception with wine and some soft drink on the first floor. There's reconvene there.
And some crisps.
Let's thank Misha.
Thank you.